A block of mass m moves in circular motion along a vertical circular track of radius r. Part A. In order for a block to remain in contact with a track at the top of the circle, determine the minimum speed it must have at the top. Before doing this question, one thing you have to keep in mind is the circular motion is still in Unit 2. So everything we talk about here are still deeply connected to mechanics or forces, or the main topic of Unit 2. So in Part A, the first thing we need to do is draw a free body diagram. When a block is at the top of the surface, it's definitely a gravitational force that's pulling it downward, right? There's also normal force that is pointing downward because it is contacting with a surface, right? And the surface must push it in the opposite direction of the pressure force that the object is exerted on the surface. So there must be a normal force that's like pushing it backward. Or another way for you to understand is that there must be a normal force preventing the object to being fly away from the track or break the track. So that may be easier to understand. So there will be a Fn. And then another thing that's important is that both of these forces are pointing toward the center of the circle, which means the sum of these two forces is equal to the centripetal force, Fc. So let's write the net force equation down. Sigma F is equal to Fc. It's equal to Fn plus Fg. Is equal to m times AC. What is the formula of centripetal acceleration? It's equal to v squared over r, right? So let's plug it in. It will be mv squared over r. Since in the question it says, it wants the block to remain in contact with the track, but minimal contact. So the Fn over here is negligible. It is close to zero, very close to zero. So we can assume it's zero, right? So let's just write Fn is equal to zero. So now let's write the new net force equation down to make it look better. Fg is equal to mv squared over r. What is that? Fg. It's equal to mg, right? So we can remove these part and put them together. mg is equal to mv squared over r. You can easily see that m can be cancelled out, right? Because both of the m are the mass of the object. So we can get, I'll write it down there, I guess. G is equal to v squared over r, which we can easily get. This is an arrow. V is equal to the square root of gr. Alright, now part B. If the block has an instantaneous speed v at the top of the circle and does not lose contact with the track, determine the magnitude of the normal force exerted by the track on the block at the top of the circle. It's still at the top of the circle, right? So we can keep the free body diagram we drew from the previous part. So let's still write the net force equation down because it's in Unit 2. Net force F is equal to Fc. The reason why it's equal to Fc, I already explained it in the previous part. And it's equal to Fg plus Fn. And it's equal to, of course, m times AC. What is AC? V squared over r. And it's equal to Vm. Now, this looks better. mv squared over r. However, now the Fn is non-negligible because we're trying to find a normal force when the object is moving at velocity v. So let's keep it like that, and then let's see which one can be replaced by the value we already know. The first thing you can see there is Fg. Fg is equal to mg, right? So we can write mg plus Fn is equal to r times mv squared over r. Well, basically it's already done. Do we know m? Yep, it's already been given in a question. Do we know g? G is 9.8, right? It's a gravitational constant. We're trying to find Fn. Do we know m? Sure. Do you know V? Oh, we already knew V. V is over here, huh? Do you know radius? Oh my, the radius is, oh, not here. Oh, the radius is over here. So, easily, Fn is equal to mv squared over r minus mg. Of course, if you want to make it looks a little bit better, of course, if you make it looks better, your teacher will love you. M times v squared over r minus g. Your teacher will love this expression, trust. Alright, that's it. Time to jump to the second FRQ.